All right, this is a video key just for the sandwich theorem. You should have already watched the video key for the rest of problem set 2.1, if you remember. So this wasn't on the original video key because this was something that was not on the AP exam, and I used to teach it every year. Anyways, and then I stopped teaching it, and then when I stopped teaching it, they put it back on the AP exam. So that's why it wasn't on the video originally. So let's put it back on there. Okay, so sandwich theorem, here's the idea from a picture perspective. If you look here, let's read the sandwich theorem first. So we have three functions where one, our function g, is always smaller than some other function f, which is always smaller than h. So graphically, that means just the graph of g is always the lowest graph, and the graph of h is always the highest graph. And the graph of f is somewhere in between those two things. So let's do a little bit of color coding here. So let's make the graph of g green. Okay, so let's say g looks something like this. Okay, so there's our function g of x. Doesn't really matter what it looks like. And then let's take h of x, and we'll use orange for that one. Okay. So, and then let's say h, which always has to be above green because it's greater than the function g. Let's say that does something like this. Okay, it's still always above it there. Then if f is always between those two things, then graphically f could do all sorts of things. It could, it can go up and down, but it's got to eventually go to where those two are going if those two go to the same place. So if blue is going to be between orange and green, so we're focusing right here. If blue is between orange and green go to the same place, then blue must go to that place also. So, let me label my graphs here. This is our function f of x, is the blue one. Okay, so that's the picture representation. Basically, if f is between h and g, and graphically h and g go to roughly the same point or same place, then the blue graph has to go to the same place because it has to stay in between the other two. So from an algebraic perspective, that's what we're going to do. We're going to try to find a function. So here, this is like our function f. We're going to try to put this in between two other functions that we can find the limit of, because then if those limits are the same, then the limit of our blue function will be the same. Just like right here, as orange and green go to the same y value, the blue function must also go to that y value. So what we can start with is a simpler version of the given function, which is x squared sine of 1 over x. If we just look at sine of 1 over x, we know that sine, no matter what, if you think graphically, the graph of sine, think about the range. No matter what you plug in for x right here, other than 0, where this function will be undefined, the value of sine of anything is always between -1 and 1, and could equal -1 or 1. Okay, so it doesn't matter what our x value is. We know sine of anything, any angle in the world, is always between, the answer has to be between -1 and 1. So then what we're going to try to do here is just rebuild this function over here, I guess right here. And so, well, that's pretty simple to do. All we have is an inequality, and we can manipulate an inequality and keep it true just by like adding the same thing to all three parts or multiplying. In this case, multiplying is exactly what we want to do, because the only thing we're missing from the given function is this x squared term right here. So if we multiply this by x squared to create the function that we're actually trying to find the limit of as x goes to 0, then we can multiply this by x squared, and we can multiply -1 by x squared. And our result is something very useful, because now we have -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. So we have now sandwiched the given function in between two other functions, right here and right here, but those two functions, we know how to find the limit of those, because those limits are just plug-inable no matter what our x value is. So we can evaluate the limit of x squared and negative x squared as x goes to 0 of negative x squared. Well, just plug in 0 because you can. Remember, that's the easiest way to evaluate a limit when possible. So that's 0. The limit of x squared as x goes to 0 is also equal to 0. So we've shown that the limit of this function and this function as x goes to 0 equals 0. Therefore, since this function is always between those two functions, its limit must also go to the same place that the other two functions go to, which is what I was trying to illustrate in this picture. Since the blue function is always between the orange and green, then if orange and green go to the same place, the blue graph must go to that place because it has to stay between those. So that's a pictorial representation. Here's a more algebraic one. If the limit of this guy is 0 and the limit of this guy is 0 as x goes to 0, since this function is always between those two functions, its limit must also be 0 as x goes to 0. And so the limit as x goes to 0 of x squared sine of 1 over x must equal 0. And that's the answer.